in summary of our results, we chose to use scatter plots to show the data. First of all, our helicopter design and pattern choice. The results of that data showed that pattern 1 had the data points at 2.2 and 2.3. Pattern 2, you can see that those were a shorter amount of time, and pattern 3 was also a shorter amount of time. This was what caused us to select pattern 1 with the wider curved blades as our choice of helicopter design. Following that, when we went to our helicopter material results, this shows each data point for our copy paper, cardboard, construction paper, cardstock, and foil. The copy paper data showed the points were 1.6 and two of them at 1.7. So very consistent results that were tight and our highest data points. The cardboard was 0.6 and 0.7, which was one of our least amount of times that stayed afloat. The construction paper was in the 1.5 to 1.6 range. The cardstock was 1.1 to 1.2 in range, and also very consistent data points. The aluminum foil was also low in terms of the time aloft, and it had inconsistency with data points. And because of the flimsy material and the design of the helicopter, we feel like that impacted the reliability of those results and those numbers being a little bit inconsistent. The cardboard, of course, just the mass of it, we feel like impacted that design. Once we determined the copy paper design was what we were going to use, or the copy paper material, we went to the blade length test. And in that part of the investigation, we took the original design, we decreased it by 1 inch, and we increased it by 1 inch, and did 3 consecutive tests on those blades, dropping those blades from the 6-foot height. With the 3-inch blades, the data was tightly between 1.3 and 1.4. With the 4-inch blade, it was also very consistent between 1.6 and 1.7 in the first trial. The blue dot shows the first trial of that 4-inch blade. The 5-inch blade in the first trial are the green dots, and those showed one point was at 1.3, 1.7, and 1.8. This spread of data brought the means very close. However, we felt like this showed some inconsistency in the design, the data. So we wanted to retest these two to get more data points and show so that we could really confirm our results. The 4-inch design again produced very consistent data at the 1.7 and 1.8 second range in terms of time aloft. This particular time in doing the test with the 5-inch blades, these were all very low, ranging from 0.6 to 0.9. Again, what we saw was a lot of inconsistency in that data, and what we noticed in that design was that the blades did not always open, and so it fell in very different ways with the longer blade length. So as a result, in our summaries, we can see that of the patterns provided, we determined that pattern 1 with the wider curved blades stayed aloft the greatest length of time. Of the materials that we tested, copy paper proved to be the best choice for keeping the helicopter aloft the longest. When testing blade length, our initial test resulted in very similar mean times aloft for the 4-inch and 5-inch blades, with great variation in the data points for the 5-inch blade. Upon retesting to collect that additional data for the 4 and 5-inch blades, the data continued to show inconsistent results for the 5-inch blade. Therefore, we determined that the helicopter with the 4-inch blade consistently stayed aloft longer. We believe this is because the longer blade design caused the blades to open in an inconsistent manner. Further questions and investigations we would have as we would move further in this inquiry would be to retest the 4-inch and 5-inch helicopters with the blades open at the beginning of the drop. We also wondered how would the length of the base affect the time that it stays aloft, in other words, the proportion of the base to the blade length. 2 other questions we also thought were that can we change the design to test the angle of the blade, and can we change this design to add blades? Those would be further tests that we might be interested in looking into as well.